In this video, you won't see any computer-generated images, only real photographs of the sun. Some have taken it for a god, others for a ball of fire. It was once thought to be the center of the world and universe. But it is only the king of the solar system. It is its center and creator. Undisputed master, it has ruled unchallenged for 4.5 billion years. Like all stars, the sun is not a perfect sphere, smooth and featureless, uniformly bright. Its tumultuous surface is the scene of perpetual turmoil. Swept by winds, waves, tornadoes, and surges cross it. Spots and lines of magnetic fields form there and break away from it. Eruptions and bursts of anger give birth to violent solar storms that quickly die out. Magnetic loops intertwine, tear, and burst. The sun is not a gigantic ball of gas either. The matter that makes it up has long since reached what is called the fourth state. It exists there in the form of plasma, a kind of soup of particles charged with free electrons and ionized atoms that can rise thousands of kilometers above the surface before falling back down. Sometimes, on the sun, it rains matter that is much hotter than fire. Since time immemorial, the sun has inspired countless myths and legends, each more wondrous than the last. Thanks to technological progress, we have discovered that it is even more fascinating than we could have imagined. And if we are able to say this, it's because today we can observe the sun through the great variety of light it emits. With this power, which allows us to see and capture wavelengths inaccessible to our eyes using telescopes, we have started to unlock the secrets of this ocean of charged particles, heated to various colors. Because each type of light we observe gives us access to different phenomena and different temperatures. Each color reveals information about the energy and heat, and it allows us to observe how matter moves on the surface and around the sun. In reality, we never see with our own eyes more than a tiny part of our star as it truly is. Here is the sun seen in the range of the most energetic ultraviolet radiation. The hazy area around the blue sun has its own wavelengths. This is its upper atmosphere, the gigantic corona of King Soleil. In this region, the temperatures are insane, because here it's about 1 million degrees on average during periods of low activity, and up to 4 or 5 million when our sun goes into an agitated mode. To observe the solar corona, you always have to focus on very high energy light. The question is why? In the sun's upper atmosphere, it's 200 to 1,000 times hotter than its surface, which is only 5,500 degrees. This question remains burning and unanswered. This corona can even be seen with the naked eye during total solar eclipses, which photographs struggle to capture accurately. The fact is that the sun's atmosphere is much larger than the star itself, extending and thinning out into space for more than 10 million kilometers above its surface. The sun's corona is an absolutely gigantic region that often extends far beyond the frame of the images, and whose boundaries fade away at distances several dozen times the radius of the star. When we look at the light emitted by matter heated to 600,000 degrees, it becomes obvious that the sun is a magnetic bomb. Because inside the corona, where the density of the stripped matter is nearly 1 billion times lower than that of Earth's atmosphere, at sea level, large numbers of coronal loops are formed. These arcs, which regularly appear on the surface of the sun, form in about 10 hours and usually dissipate in just a few days, at most. Although some may exceptionally persist in the corona for several months. These coronal loops can reach truly gigantic sizes. The smallest of them are several thousand kilometers long, while the largest stretch hundreds of thousands of kilometers above the surface. You can truly appreciate their size only when you place our planet next to them for scale. Along these arch-shaped magnetic field lines, streams of erupting solar material are channeled and accelerated to the point where, in these loops, flow speeds reach nearly 100 times the speed of sound. If matter is constantly set in motion on the surface of the sun, it's because our star is a dynamo of staggering complexity. Within it, electrically charged matter, dancing on and beneath the surface, generates the formation of intense magnetic fields. These magnetic fields, in turn, tell the matter how to move. Matter whose movement once again influences the magnetic fields. I think you get the idea. The loop is complete. Because the solar magnetic field, unlike that of our planet, is continuously in motion. Unequal, dynamic, and fluid, it is made up of immense regions of opposite polarity, within which move quantities of electrically charged matter whose mass far exceeds that of. This loop presses its ends onto regions subject to opposite magnetic fields, serving as the sun's entry and exit points. That the coronal loops rise above the surface. The loops are moving prisons for the matter circulating within them. Because the charged particles of the plasma inside can only move parallel to the magnetic field lines. And this surface chaos is further intensified by the rotation of the sun itself, a rotation whose speed is different at the equator and at the pole. Because our star is not solid, all these regions do not rotate at the same speed. Matter at the equator rotates in 25 days, while matter at the pole takes 35 days to complete a rotation. We were even able to deduce this by studying the vibration modes of the matter on the surface. The rotation speed of the star's core, which must complete a full rotation in just under a week, is nearly 4 times faster than the outer layers. And this incessant mixing of matter in the sun contributes to distorting, weakening, or strengthening the intense surface magnetic field, whose lines are disturbed, broken, and reformed in a continuous process of reconfiguration. During periods of high solar activity, you can even see series of active regions aligning, connecting with each other as they begin to share their chaotic magnetic field lines. At times, the sun's surface experiences intense eruptions under its hot atmosphere. These colossal explosions are generally triggered when, following a phenomenon of magnetic reconnection, the fields distort and reorganize rapidly, suddenly releasing an excess of accumulated energy. They then erupt over several thousand kilometers. Giant explosions of matter and radiation that can be observed by our telescopes across all ranges of the electromagnetic spectrum. And the same eruption can look different depending on the wavelength ranges observed and the combinations of mixed lights. In the wake of these brief and violent bursts of light, matter torn away from the sun at high speed by magnetic field lines then rises to several 100,000 kilometers above its surface. Here too, placed next to these towering plumes, our world looks insignificant and allows us to grasp the sheer scale of these massive eruptions. While most solar eruptions last from a few dozen seconds to minutes, the most powerful ones can last for several hours. The spewed out plumes are so vast that they wouldn't fit in the distance between Earth and the Moon. These colossal solar eruptions are often followed by the explosion of gigantic thermal bombs called coronal mass ejections. These kinds of solar hurricanes form when the magnetic fields running through the corona cross, twist, and tangle together. Eventually they snap and violently realign. And when these magnetic bubbles, which can reach several million kilometers in diameter, become too stretched and finally burst, hundreds of millions of tons of plasma are then propelled at incredible speeds across the solar system. To fully grasp these events that can tear part of the star's atmosphere away, you have to step back and block out the sun. Even protected by our Earth's magnetic field, which acts as a shield. The most powerful of these coronal mass ejections, if they hit our planet, could temporarily send our industrial civilization back in time. Back in the candle era, we were even exceptionally able to observe, in this turbulent atmosphere, the formation of solar tornadoes, magnetic structures swirling around themselves 300 times faster than the speed of sound. During solar eruptions, however, the vast majority of the matter torn from the surface of the star will simply end up temporarily feeding its atmosphere, before eventually falling back down. In this video, covering 4 hours of activity, you can see that a large part of the matter flows back toward the sun, injected into the corona, by powerful solar eruptions that lift the plasma in spirals to hundreds of thousands of kilometers in altitude, sometimes triggered by medium-sized eruptions. We also observe the formation of strange and long filaments that, after erupting from the sun, seem to float above its surface. This one, 800,000 kilometers long, was captured winding along nearly a quarter of the sun's circumference. And I think we need to pause and put the Earth next to it to really grasp its enormity. These filaments are elongated clouds of cold plasma with temperatures in the tens of thousands of degrees. They appear dark compared to the material making up the corona in which they evolve, and which on average has a temperature close to 1,000,000. Held above the solar surface by powerful magnetic fields, these filaments rise, expand, and stretch over several thousand kilometers. They form over periods of about a day and can persist in the corona for several weeks or even several months. Some of them even manage to make several trips around the sun before eventually deforming, breaking apart, or dissipating. Inevitably, the matter contained in these filaments, just like in the coronal loops, always ends up falling back onto the sun in the form of a rain of fire and plasma. And that's why it sometimes rains on our star. When the magnetic field that creates the coronal loops weakens or breaks, the matter, which is denser than its surroundings and was trapped there along the lines of force, then starts to fall, dropping down from the upper atmosphere. And gigantic amounts of plasma then shoot toward the surface, which they will eventually reach. After a few hours of a dizzying fall. The video you are watching has been sped up to fit 22 hours of coronal rain into just a few minutes. Jets of solar material falling back can sometimes even be seen in red on the edges of the sun during eclipses. All of these immense trails of plasma, these filaments and coronal loops that get lost in the corona, also injects a lot of energy into the sun's atmosphere, and in doing so helps to fuel the solar wind. That is the small portion of plasma that is fast enough to escape the gravity and magnetic field of the sun. These gusts eject into space an average mass equivalent to the Pyramid of Khufu. Every 4 seconds, they often take the opportunity to escape through the presence of holes in the solar atmosphere. These huge dark spots that can be seen when observing the sun in the extreme ultraviolet and X-ray wavelengths are coronal holes, weak areas that can move and migrate over time, and through which the underlying burning matter, pushing to escape from the star, rushes out. Vast regions of the solar magnetic field with a single polarity create these dark-appearing holes, because they have a lower density than the surrounding plasma and therefore offer less resistance to matter trying to escape. In these regions, the star's magnetic field lines do not form loops that emerge from the surface and dive back in, but are open and shoot outward through the solar system. Thus, it is through these gigantic dark areas, large and deep enough to fit our planet dozens of times, that a large part of the charged particles making up the fast solar wind are able to burst out into space. In this close-up, taken of a coronal hole that formed near the sun's south pole, you can see the continuous outflow. Charged particles that take advantage of the low density of the solar atmosphere and the favorable orientation of the magnetic field to leave our star. By moving away from the high-energy lights, we can start to approach the details and features that previously escaped us. You are looking at a transition zone, an extremely thin layer of matter, barely 100 kilometers thick. The matter in the image bubbles at temperatures below 10,000 degrees. And to be able to see its movement, nearly 9 hours of solar activity have been sped up to fit into just 30 seconds. Below this region, we leave the corona to enter the chromosphere, the lowest and coldest part of the solar atmosphere. Within this layer, which is about 1,000 kilometers thick, temperatures gradually drop as we get closer to the true surface of the sun. So much so that at its base, it is mild enough for matter to leave the plasma state and for simple molecules to form. Thus, spectral signatures of carbon monoxide and even water vapor have been detected in the chromosphere. There is a small amount of water on the sun's surface. In these images, the sun would almost seem calm. But solar eruptions here can exceptionally cause the formation of Morton waves, a kind of shock wave. Stellar tsunamis that spread and transfer energy from one region to another, via plasma waves traversing the chromosphere at 500–931 miles OSC. It is also at the base of this region that the amazing spicules are formed, plasma filaments that rise chaotically and continuously at high speed. Like a fiery mane with strands about 500 kilometers in diameter and around 10,000 kilometers in height. These spicules, the tallest of which are as wide as our planet, exist for only a few minutes at most before falling back and disappearing into the chromosphere. Then immediately they are replaced. It is believed that there are nearly 3 million spicules constantly waving near the surface of the Sun, where hundreds of millions of nano-eruptions, each a few hundred kilometers high, have also recently been discovered. At most, these miniature eruptions, which are constantly igniting on the surface of our star, would heat its atmosphere from a distance through the waves they emit. And in doing so, with the coronal loops that, as they rise into the upper atmosphere, inject large amounts of energy there. They are among the main suspects for explaining the huge temperature gap between the surface of the Sun and its corona. Finally, beneath the chromosphere, we can at last see the true surface of King Soleil. The photosphere, which when seen in visible light, gives the impression that our star is a perfect, featureless sphere. The surface of the photosphere is almost only marked by the occasional appearance of sunspots. If these areas are darker than the surrounding material, it's because, strangely, their temperatures are around 3,500 degrees Celsius, while the average temperature here is 5,500 degrees Celsius. These spots, which during their existence move, merge, separate, rotate, or disappear, can change shape in a few hours or remain stable for days or even entire weeks. Some develop very quickly on the surface of the Sun, and small emerging spots can, in just a few days, change in size, from the size of a land continent to 4 times the size of our planet. Often, the presence of these sunspots is a warning sign of an impending outburst, because the frequency of their appearance, as well as their size, gives us precise indications about the strength of upcoming eruptions. The shadowy areas on the Sun are the starting points. They form in regions where particularly strong magnetic fields accumulate, as you can see by changing the category of light being observed. It's this intimate connection that unites them. The intensity of the magnetic field explains the surprising temperature difference between sunspots and the surrounding solar material. It is believed that, directly beneath these dark areas, the magnetic field actually prevents the hotter material from rising up from the depths of the Sun. By moving up into the range of light waves that allow us to observe the chromosphere, we can see thousands of brighter, speckled cells appearing around the edges of sunspots, each one measuring several thousand kilometers in diameter. In these images, if both the chromosphere and the photosphere appear visually grainy everywhere, it's not due to a flaw in the image or background noise. These disturbances are also not caused by aberrations, but by the hundreds of thousands of solar granules that are born and die in just about 15 minutes on average on the surface of the Sun. And so, in these time-lapse films showing us solar activity over several hours, these constant swirls make the surface shimmer. Looking more closely, we can see that these myriads of granules, which give the photosphere the appearance of a mottled orange peel, are shaped by convection cells formed by the constant upward movement of hot plasma rising from the depths of the Sun. Before cooling slightly and then, immediately after, plunging back into the star at the dark areas surrounding each cell. The scale of surface turbulences can be hard to comprehend. Each one is as large as a country like France. So, an image like this covers a part of the Sun large enough to fit our planet 4 times in a row. In this other film, you can see 10 minutes of the Sun's surface bubbling, sped up to make a video of just 5 seconds. Some regions located between the boundaries marking the edges of the convection cells are particularly bright here. That's because they reveal deeper and hotter parts of the star. In a way, they're like dives into the stellar landscape. By observing an increase and then a decrease in the number of spots over time, we were able to begin to grasp the mysterious rhythm of the Sun. Because the frequency of the appearance of spots that pepper the surface of our star, as well as the solar eruptions that rage there, follows an 11-year cycle, a duration whose underlying reason is still unknown. During the maximum phases, the surface of our star, richly covered with spots, can be subject to several eruptions per day, whereas during these phases of minimal activity, there are practically no spots present. The Sun experiences no more than 1 eruption weekly. By closely observing the roughly 21,000 solar eruptions and 13,000 coronal mass ejections recorded during the last cycle, it was also found that our star often gets agitated in the same place. In this photo, you can see the areas of the star that, over the course of a year of activity, were the most agitated. It is believed that these particularly active regions, where eruptions are much more frequent than elsewhere, are solely responsible for emitting 3/4 of the energy that gives the solar atmosphere those dizzying temperatures. And if we can say that the photosphere is, strictly speaking, the true surface of the Sun, it's because beyond this sizzling boundary, which is only about 400 kilometers thick, the plasma becomes so dense that it changes from transparent to opaque to all types of light. In other words, beneath the photosphere, technically, we've entered the inside of the Sun and the blazing hot inferno is plunged into total darkness. To venture further, to probe deeper into the Sun's interior, there are no more images, only models, which tell us, through the surface movements we observe, that it exists. Below, there's a convective zone where immense swirling bubbles of plasma rise up. Taking nearly 10 days to rise from the great depths, these bubbles draw their energy from an even deeper zone, the radiative zone. A region so hot and dense that heat transfer occurs only through thermal radiation coming from the core of the Sun. A central region where, in barely 1% of the star's total volume, nearly a third of its mass is compacted. And where the matter is so agitated and compressed that temperatures reach 15 million degrees. Within this furnace, whose volume spans the Earth-Moon distance, the Sun generates all its energy, at great cost of nuclear fusion. Every second, these 4 million tons of matter are vaporized, and this has been happening non-stop for 4.5 billion years. Since our Sun ignited, 4% of its total mass has been transformed into a colossal amount of energy. An energy emitted in the form of radiation that struggles to escape from the Sun. Because the central region is so dense that every single ray of light is almost instantly and constantly reabsorbed, re-emitted, absorbed, and re-emitted. In a continuous game of billiards, where each particle of light must at random find its way out. And it's only after an average journey of 170,000 years that the photons finally reach the surface of the photosphere. Finally, they blast off into space. Well, 8 minutes and 20 seconds after leaving the Sun on their way to our planet, a tiny number of them land on the surface of your cone. In your eyes, the next time the light of the setting Sun reaches you, I hope you'll see the Sun in a new light. Because even though our star is an ordinary yellow dwarf of spectral type G, like more than 100 million others in the Milky Way, it is still a fabulous star among so many others. The most important and incredible one, because it's ours. And just to try to leave the immensity of our star engraved in the back of your mind, I'll leave you with a few transits of the closest planets to our Sun. In these images, even though Mercury is 58 million kilometers closer to the telescope's lens that captured its passage than our star is, there is nothing new under the Sun. Within our system, nothing can truly overshadow it. Share the Sun with me so it can shine for everyone, not just yourself.